Hi there, welcome to this short video on the investigative steps that we can take when a circuit fails its ZS max values utilising the rule of thumb calculation. Okay, so that's where it fails its on-site guide's ZS max value. Okay. Now, the example we have here, we've got a ring final socket circuit. It's in an office. It's had a measured earth fault loop impedance of 1.18 ohms. At the origin of the supply for this circuit, we have a 32 amp type B MCB, and after some further investigation, we identify that the external earth fault loop impedance, the ZE value, is 0.37 ohms. Inside BS7671, table 41.3 for circuit breakers, we have a ZS max value for this type B MCB, this 32 amp type B MCB, of 1.37 ohms. Okay. Now, in the on-site guide and on table B6 for this 32 amp, same 32 amp type B MCB, we have a rule of thumb max value of 1.1 ohms. Okay. Now, it's not quite rule of thumb, but close to rule of thumb value of 1.1 ohms. Okay. The 1.1 ohms is taking into account that the circuit that you have just tested is sitting at ambient temperature, whereas the BS7671 max values, that 1.37 ohms, is taken with the circuit fully loaded, okay, so under load conditions, all right, where it's sitting at 70 degrees C, okay. So you'll see there the ZS measured value of 1.17 ohms is more than the on-site guide max value, but it is less than the 1.37 ohms from BS7671. Okay, now the only time we would ever carry out further investigation for a circuit that fails its earth-fault loop impedance from the on-site guide max value is when it falls in between these two values. Okay, if it's beyond the 1.37 ohms, then there's no point actually carrying out this calculation. So it's only when it falls in between these two figures. Okay. So what's the first step that we have to take? Well, we've got a measured ZS of 1.18 ohms, okay? That 1.18 ohms is at 20 degrees C, okay? So the first thing we have to do is we have to extract the R1 plus R2 value from this ZS value, because both of these values are at 20 degrees C, okay? So first thing we do is we take our R1 plus R2 value at 20 degrees C, to find our R1 plus R2 value at 20 degrees C. We take our ZS at 20 degrees C and we subtract the ZE, the external earth fault loop impedance. Okay. So 1.18 ohms minus 0.37 ohms, that gives us an R1 plus R2 value at 20 degrees C of 0.81 ohms. Okay. This 0.37 ohms, the ZE, the external earth fault loop impedance, we have no control over it. When we applied our correction factors to the on-site guide values, we applied those correction factors to the entire earth fault loop impedance, the ZS value. Okay. This ZE value, we are going to assume is actually still sitting at 70 degrees C. Might not necessarily be that leg of the cable that's coming into your property, but in the street, heading back to the substation, it's sitting at 70 degrees C, okay? So what we have to do is we have to take this 0.81 ohms and we have to bring it up to the same 70 degrees C that we're expecting this external earth fault loop impedance to be sitting at, okay? So how do we do that? Well, copper, if you look in your on-site guide, your guidance note 3 in your on-site guide, it's appendix I. In your guidance note 3, it's appendix B. You'll see on underneath the second table, there's information about the positive temperature coefficient that copper has. So the positive temperature coefficient that copper has is 0.004 ohms per ohm per degree C at 20 degrees C. All right. So as we increase from 20 degrees C, we apply this factor to whichever resistance value that we're dealing with. So if we were measuring at 10 degrees higher, I would use a factor of 0.04 as my correction factor. So if it was rather than 20 degrees, it was sitting at 30 degrees, I would use 0.04 rather than 0.04 because we've had an increase of 10 degrees C. But you'll see here, we are looking for the difference here between the 70 degrees C max rating of that cable and its measured 20 degrees C. So 70 minus 20 gives us 50 degrees C. We take that 50 degrees C and we multiply it to that 0.004, and that gives us a correction factor of 0.2. Okay. Now, in your regulations book, in Appendix 3, it tells us that on site we use this rule of thumb where we're taking that 70 degrees C, that hotter cable's ZS max value, and we apply these correction factors to it to bring it down to 20 degrees C. So we multiply our BS7671 max values as a rule of thumb down by 0.8 to bring it down to our max value that we can accept on site when we're carrying out these tests. Okay. Now, we have already measured it at 20 degrees C. So what we need to do with this R1 plus R2 value that we've just calculated in the previous step at 20 degrees C, we need to bring it up to 70 degrees C. So we use that same factor, but rather than taking it off of 1, yeah, because that's what we do here, we take that 0.2 off of 1 to bring it down to 20 degrees. We're going to go from 1 at 20 degrees C and take it up to 70 degrees C. So we're going to multiply by a factor of 1.2. Okay. So we take that 0.81 from the previous step and multiply it by 1.2. It gives us a new R1 plus R2 value of 0.972, but that's with the R1, R2 value sitting at 70 degrees C fully loaded. Okay. So after this, step 3, we have to calculate a new ZS, and that new ZS is at 70 degrees C. So we just carry out a normal earth-fault-loop-impedance calculation. We take, to calculate our new ZS at 70 degrees C, we take our ZE value and we add it to our R1 plus R2 values at 70 degrees C. So we take the 0.37, add it to 0.972 from the previous step, and that gives us a new ZS value at 70 degrees C of 1.342 ohms. So now that we've corrected that cold cable or that ambient temperature cable and brought it up to full load conditions, we can see there we have a new ZS of 1.342 ohms. As we noticed, we identified earlier, BS7671 has a max value for this circuit at 70 degrees C of 1.37 ohms. So our further investigation has identified that this circuit actually passes the ZS max. Okay, so if you're doing this for an initial verification, if you're doing this for a periodic inspection,